A1, the average. Okay. In order to find the natural frequency, you're going to solve for the eigenvalue. Okay. So this is the expression. So you do the expression up. Okay. Then you can find this is the natural frequency. Okay. 1 is for 0, and 1 is for square root of 12k over m. OK， 看到没有？这个算法 ，OK， 是假设它是一个U1 不受约束的情况 ，OK， 不受约束，它可以自由振动，所以整个连杆它可以上可以下，跟它自然频率是0。它变成OK， 另外一个情况是开根号12k 除以 m， 所以你可以想象，这个跟我们的直觉好像有点出入。以前不是说那个自然频率是开根号 k 除以 m 吗？为什么这个时候变成12倍 ？OK， 开根号12除以就是开根号 k 除以 m， 那个是建立在一端固定，另外一端拉扯。然后释放 ，OK， 这个呢就有点像悬浮在空中的一个连杆。第一阶是0，这个是第二阶比较高阶 ，OK。So now let's come to the example. Okay, if you now want to find this to find out the natural frequency, let's divide that into 2. Then you have these 2 stiffness matrix, and you can now do the exact-ring. OK， 这个主动我跟大家过一次，你们自己去装 OK。然后you can find out the stiffness matrix and the mass matrix after the exact-ring look different. When they look different, they look like this. Okay. Then because of the boundary, U1 is 0. So now you only keep the U2, U3 related stiffness matrix and related mass matrix. Okay? And in this way, you can find the natural frequency. After you have obtained the truncated mass matrix times acceleration vector plus truncated stiffness matrix times displacement vector equal to 0, you can now assume harmonic responses and then do the substitution in. Then you can find the natural frequency. And what are the natural frequency? One of the natural frequency is 0.1 square root of k over n. The other one is 1.32 times square root of k over n. Okay? 所以这是通过你这个矩阵的。Okay? But what is your gamma? Your gamma is defined as 4e over rho l squared. Okay, that's for the simplification. 所以通过这个方式，你就可以找到一根这个叫做连杆，它的自然频率 ，OK， 这是自然频率是跟它的杨氏模数，跟它的密度相关，杨氏模数的密度比，然后这个呢是跟它的强度的反比 ，OK， 然后这个系数取决于第一阶还是第二阶的动态。Okay, this is now the vibration along the rod. Okay, so this vibration along the rod, okay, is what you call the solid wave propagation. Okay, 这是在一个固体连杆结构上的一个驻波的这个频率。Okay， 它不是像我们是一个弹簧。再加一个质量，这个是一个单纯固体上面的一个驻波，而不是也质量跟线性场。Okay, so now next we're going to do some extrapolation. What's the extrapolation we're going to do? What happens if you now have a 2D rod? Okay? If you now have the 2D road, okay, so you have 2 degree of freedom, okay? Then you don't just have the velocity in the x directions, you have the velocity in the y direction. How do you write the energy form? 这同学，如果你要写这个一个连杆 ，OK， 它是斜的，它有一个水平位移、垂直位移 U1、V1，然后下面一个是 U2，然后 V2，OK。If now I put U and V as a displacement, and then the velocity will be U dot 1, V dot 1, U dot 2, U dot 2. What will be the kinetic energy? Okay? So if you're going to do interpolation, again, your U1 is in your U at any point is N1 U1 plus N2 U2. And then your V at any point is equal to N1 V1 plus N2 V2. How do you write your kinetic energy? Your written of the kinetic energy is very simple. This is like what we did just now. I'm doing the integration of horizontal velocity squared with respect to the length. Okay? So how to write the energy form? Okay, I write it over here. So let's 把这个动能写下来。OK， 写动能有一个好处，基本上，反正你给定的坐标，你就把那个速度做一个平方乘上质量，然后另外一个方向的速度也直接平方乘上质量就好了。反正这两个速度只要是正交，这个你就不需要做任何分解。So how to write the kinetic energy? The kinetic energy is, if you single mass, it is n u squared, u dot squared plus half m v dot squared. Okay? If this is a single mass, 如果这是一个点质量 ，OK， 它有 u v 的这个正交的这个速度，这就是它的动能了。But now what you have is a rod. Okay? So if now what you have is a rod, you have u dot 1, v dot 1, u dot 2, v dot 2. So you're not going to write this way. What you have to write is, you're going to write the integration. Integral u dot squared vm plus integral v dot squared dm. And what is your u and v? Okay, your u and v, okay, almost as what you did. Okay, you can write them as integral u dot transpose n transpose and then u dot. And then dm, what is dm? dm is rho a dx. Okay, and then this one is half v dot transpose n transpose n and v dot rho a dx. Okay, what is your n? Your n is, okay, because your n is defined, okay, because your u at any point is defined as your n1, n2, n3 times u1, u2, u3. And then your v, likewise, is your n1, n2, n3 times your v1, v2, v3. 通过这个方式 ，OK， 你可以把你的矩阵写出来。不过因为它是正交的关系，所以你这个跟刚才的解法一样。OK， 你把它展开来 ，OK， 展开过后，你发现，反正它都隔开的，无所谓。就好像这个隔开的，这个是变成了N1，然后这个是 This is the entrance for your velocity. Okay, let me show you. This is for the block it up. Draw the square. So this is the entrance. Okay, this is the association with your velocity in the horizontal direction. The next one, let's change the color. The blue one. So this is what we're going to tell you. Good thing about this consistent mass is, yeah, basically the kinetic energy in the x and y direction, they are orthogonal. Okay, they don't interfere with each other like spring. Okay, so you can simply put them in the respective position. Okay, so 现在你们家的脾气也是，然后 so in a nutshell, so this is your kinetic energy in 2D plane in the x and y direction. Okay? For simplicity, if you go and add them up, row entry, sum them up and put them into the diagonal term, this is going to be 3. Add them up, put it on the diagonal, that's going to be 3. Okay? Add them up and put them into diagonal expression is going to be 3. So this is the diagonalization of the mass. If you want to cut short your determination of your eigenvalue and eigenfrequency. Okay? Okay? So how about the transformations? For velocity, you don't need to transform anyway, because kinetic energy is going to be sum up, u squared, v squared. The end up going to be constant. Okay? Only part that you need to do the transformation is your status. So this is telling you if you're going to do the transformations, nothing much is changed. Okay? So in short, your mass matrix is unique in respective of the coordinate. Okay? And in this way, if you go back and apply to your this early work, okay, your first hands-on, then you can find out the natural frequency of your structure. So this is the basis in determining the structure's limit. So once the structure is being excited close to resonant frequency, it's no more structure. It's going to vibrate excessively. Okay? So that's the idea. So what next? Next, we're going to cover your consistent mass matrix. Okay. For your constant strain triangular element. 我们来现在来看一下，如果你现在不是连杆单元，你现在是一个平面单元，它的动能是多少 ？OK， 其实这个做法跟刚才差不多是一样的，我们都是从动能的定义来做，而且我们动能是 x 方向的位移 ，x 方向的速度跟 y 方向的速度，因为是正交，所以你也无所谓 ，OK。If you now have a triangular element, we know the shape function is more complex, okay? But now, if you do this interpolation, you now have triangular element, you have not 1, not 2, not 3. Spell it up. Hello. Okay? 所以现在是从一维变到二维，二维的时候，你这是一个面，所以你3个节点。每个节点有2个方向的位移跟速度 ，OK， 一个是 x 方向，一个 y 方向，位移 x 方向是 u，y 方向是 v，OK， 节点1、节点2都有 ，OK， 你可以用内插的方式，在这一点的速度都可以用节点上的这个位移找，这一点的位移都可以用节点的位移找出来。为了内参有3个这个形状函数，一个 n1、n2、n3，OK， n1、n2、n3应该可以画出来。然后，如果相对时间变化 ，if you now take differentiation of the displacement, then your displacement becomes velocity, but shape function doesn't change. So the interpolation of the nodal velocity remains the same using the same shape function. Likewise, for the interpolation of the vertical velocity, you are still using the same interpolation function, except the nodal velocity becomes vertical. Okay. Now next, how do you find your expression? Okay. 所以跟刚才的做法一样，这里再重抄一次。你现在如果是一条线，你的 interpolation function 写的是 n1 u1 n2 u2， 但是你如果是一个面 ，OK， OK， 这个时候就变成 n3 多加了一项。So how do we write the expression for the energy? Kinetic energy is similar. Okay? If I write the short form, it's similar. Okay, now we're going to write the short form. Okay, this is kinetic energy is equal to half the horizontal velocity square plus vertical velocity square times the n. Okay, what is the n now? The n now is no more. The n now is no more the AEX. The n now is, what is your dn? Your T dA. You are integrating it over this area. Okay? And then T is your thickness. Okay? So now what is your U1? U square? Your U square? Your U is actually N matrix. Okay? U. Okay? U square is then N transpose, and then U transpose. Okay? And then what is about your V? Your V itself is N matrix and V vector. You want to make it square, you pre-multiply by the transpose. Okay? 所以通过这个形式 ，OK， 你去做积分。 OK， 要积分的部分是什么 ？BA times D，this one T，and this one BA。Okay, in this way, if you assemble them together, you can assemble them in such a way that, okay, not forget your row, the row T. Okay, then you have your half, your this U1, B1, U2, B2, U3, B3 transpose. And then this one is U1, B1, U2, B2, U3, B3. Yeah. And this is your mass matrix after you do the integration. Okay? Likewise. Yeah. But now the integration is n1 squared. Okay? Yeah. And then the A. And then you got the weight. Okay? And then this one is n1, n2, the A. And then this one 0. And then this one is n1, n3 integration the A. Okay? Let me make some more space. Okay? And then 0. And then this one is U1, B1, B2, B2, B3, B3. Okay? In this way you do the same. Okay? So this one is your n1 squared dA 0. And then this one is your n1, n2 dA, and then 0. And then this one is your n1, n3 dA. And then you repeat the same. Then this one is your integral of the n2 squared dA. Okay? And then you repeat the same. 所以通过这个方式，你去做积分，看到没有？就是 n1 square，n1 n2，然后这个 n1 n3，第二行还是重复一次，只不过一次错换 ，OK？ 然后第三行就是 n1 n2，然后 n2 square，n2 n3，然后 0，然后这个第四行还是叫做交错，跟第三行有交错。然后第三行就是再读这些一次。So in this way, now you got your stiffness matrix. Good thing about this is you are very fortunate. The form always look like this for constant strength triangular element. So you do need to do your integration by yourself. Okay? So the form is rho A. Rho is the density. A is the triangle area, T is your thickness, divided by 12. The diagonal terms are all 2. And then the off diagonal term, okay, after every spacing you got 1. Okay? So in this way, you can find your vector frequency and motion. So just take this as example. I will now collect your homework and then I will go through with the answers. 你们已经交了现在可以交吗？还是你要周三？作业现在交吗？还是你要周三再交？啊？周三了。那第一期就跟你们讲，第三题怎么解？Okay. Since okay, but you need to go back to try your homework number 1 and 2 1 because that will be the basis. Okay. Okay, I go through with you. So make sure you submit the homework. The resume. Okay. Okay, let's see your homework 3. Okay, how to solve your this homework 3? It's going to be very tedious. Here I don't put the number. Okay. B if you now have a rod subjected to, let's see the question further. Okay, this is a question about constant strength triangular element. Okay. And then your boundary and your forces appear like this. And then you are dividing them into the equation number here. Okay. How do you find the answer? OK， 给你们算是一个简介。我的这个答案是没有数值的，全部都是符号题。Okay, now you have a rectangular plate, okay, subjected to uniaxial force. Okay, now you are going to analyze it using two triangular elements. Okay, I will tell you which are the first element, which are the second. I will even give you the notes, okay, in the final exam. Okay, why I have to give you? To have a consistent answer, okay? 一定要给你，不然的话，你们的这个答案五花八门，我不懂怎么看。所以每个单元的节点都给了 ，OK？ 然后你把它分拆 ，OK？ 单元的顺序 ，the nodal connectivity must be sequenced counterclockwise. So this is how your equation was derived. If you're going to use it clockwise, sorry, the size of your sequence matrix will all be corrected. Okay? So take for example, if I took element 1, I have not 1 being real 1, not 2 being real 3, not 3 being real 2. The sequence is element 1 has the not 1 being 1, not 2 being 3, not 3 being 2. Okay? So you have to pay attention to the exact coordinate. Okay, let me see the coordinate. Where's the coordinate? Yeah, coordinate is there. The coordinate of x1 is 0, y1 is 0, x2 2l, y2 l, and x3 0, y3 l. Okay. Yeah. So being a knowledge of your this coordinate, now you can define what is beta 1. Beta 1 is actually the shape function 1. Okay, not completely full, but it's giving you y23. y23 is y2 minus y3. And then you check y23. 23 is based on the sequence, not the real nodal condition. This is 1, 2, 3. Okay? 2 is 2L. 3 is, sorry, this is y23. This is L. Okay? 3 is also L. L minus L is 0. And then gamma beta 2 is y31. Why is 31? In the sequence, this is 3 and this is 1. So the difference of the height is L minus 0. Okay? And beta 3 is y12. y12 is the height difference between 1 and 2. Okay, even though this is written as 3, but in my sequence, this is not 2. Okay, you have to make this table, make sure that you got consistency. So this is y1 minus y2. So the height of 1 minus the height of this. So the height difference is minus L. Okay? Likewise, you do the gamma 1. Gamma is x32. It's not 3 location is x minus not 2 locations in x. So this is 3 minus 2. So it is 0 minus 2L. So this is negative 2L. Gamma 2 is 1 minus 3. 1 minus 3. So this is 0 minus 0. Okay, and then gamma 3 is 2 minus 1. Position 2 minus position 1. So this is 2L minus 0. So in this way, after you got this, okay, go back to your lecture notes. Okay, so single out the degree of freedom which is free. Okay, in this case, the anchors are all bounded. So this is real degree of freedom. U1, V1 is 0. U3, V3, 0. This is actually 2 line. Okay, it's going to be consistent. Check it out. Okay, but in terms of the sequence, okay, in terms of the sequence, okay, let me rewrite. Okay, yeah, okay, so this is the real coordinate. Eh? This is the real coordinate. But the sequence is 1, 2, 3. The sequence is 1, 2, 3. Okay? Because these two nodes are fixed, no displacement. So you only need to single out the row 3 and row 4 and column 3 and column 4, which is non-zero. Okay? And then you have these elements force balance. Okay, I purposely write this element force balance to make sure that you know the correspondence. If you don't have this correspondence, you cannot solve. Okay? Also, let me see. I take this multiplication sign again. Okay? To make sure that you are not confused with the cross product. Okay? 所以看到没有？这一个东西长得很复杂，在这里画整了过后，所以 if you substitute in beta 2 and gamma 2 into the expression, or so-called the y31 and y13 into the expression, okay? Then you're going to have this simple matrices, okay? Quite a simple form, diagonal form, okay? Then next, okay, in your textbook, the other textbook, that could be written differently. They tell you beta and gamma, blah blah blah, and the sequence is different. The sequence here is U1, U2, U3, V1, V2, V3. Okay? In this case, you've got to single out the term which is non-zero. Non-zero association with the non-zero displacement, association with non-zero displacement, association with the non-zero displacement, association with the non-zero displacement. And then after the extractions, you got this expression. And then upon the substitution, you got a different expression. And then, but eventually they are the same as we did find out. We did find out, okay? Now we come to second element. Okay? Second element is tedious. Okay? In this second element, what do you have? You almost need the same, but now the second element is not 1 at the bottom, not 4 at the bottom, not 3 at the top. But in terms of sequence, this is 1, 2, 3. So you can see 1, 2, 3. And then you have your coordinate for each node 1, 2, 3. And then after doing the substitution in, okay, good thing is, yeah, here is a little bit difficult now because in this element only one knot is fixed. That is x1, y1. Okay, that's the first knot. Second knot is free. Third knot is also free. So you've got to take out these whole 4 by 4 matrices. Okay? After you take out these 4 by 4 matrices, okay, now you do the substitution. Because you know it's involving y3 1, y1 3, y1 2, y2 1. Luckily, some of them are 0. So it happens to be many terms. Okay, then you sub in. After substitution, you got this simplification. Okay, it becomes et over 1 minus b squared, 1 over 4 times the area. The first row is L squared, 0 minus L squared, 2b L squared. Likewise, luckily after doing the simplification, we got this. Okay? The purpose that I do this by symbolic is just to give you the real understanding and sequencing the procedure of solving. If you play with the number, it's too tedious. Sometimes you don't even recognize the pattern, but if you do with the symbol, at least you can do pattern recognition and see something. So, but this expression is still complex with the L squared. So I now take the L squared out. Okay? So my matrix is becoming a pure number. Okay? And now I have element stiffness like this. The two element stiffness associated with 3 degree of freedom are, okay, for element 1 is a 3 element is 3 knot is not 3. For element 2, the 3 knots are 3 and 4. So as a result, your stiffness matrices appear different. Okay? And then now you want to combine them together. When you want to combine them together, please recognize the degree of freedom. This is the 1, 2, the 3, U3, B3. But in this element stiffness force balance, element force balance, U3, B3 is at the bottom. Okay. So you got to put this row, put this 1, 1 position to the 3, 3 position. This is 2, 2 position to the 4, 4 position. So you need to know how to do the addition. Okay, after doing the addition, your matrices appear like this. Okay, this is a 4 by 4 matrix. Nobody teach you how to do the solving, but I guess you learn your engineering mathematics. 你学过点公数的，这个线性代数，这个一次的4元方程式怎么解 ？OK， 这个还好，考试的时候会给你正三角形的单元。If I give you the right angle triangle, it's quite easy to solve. So long as it's not the irregular triangle. Okay? 看一下这个正三角形的单元。Okay, this is only the stiffness matrix solved. But I still haven't told you what are the forces. Okay? After assembly. Okay? Now if you are going to do the solving for forces, okay? You need to know the uniform loading. Okay, let's see. So in the case when you have the uniform loading, okay, what do you need? You need to know the shape function where the force is applied. Okay, here the force is applied on edge 2, 3. Okay, and then the work done by the force will be stress times the horizontal displacement. And to make the stress to be coming forth, I will have Px times the incremental length 2, 3. So this U can be expanded out as a U1, N1, U2, N2 plus U3, N3. But I got to integrate along the length N2, 3. Okay? So what is the S23. S23 is basically the y here, okay? So I can later do integration, okay? But the important thing is the work done by the distributed force. If we're going to make a lump force, I have to differentiate the work done with respect to the displacement at the node, okay? So in the end, this distributed force is half this normal force is half the total distributed force. Likewise, if you do the same, okay, it is half of that, okay? 所以你这个你可以去解 ，OK， 这个你可以回头去看 ，OK。基本上你要找你的那个形状函数，你可以查找你的那个形状函数的这个公式。当然，形状函数你如果说觉得用公式太难，你就用它的定义。定义就是你 n1 一定是1，然后其他点是0 ，OK。所以你先把其他点这个0的这条线找出来。带入这个点非零的这个位置，然后设定它为1，强迫它为1，你就可以找到你的形状函数。If you want to find the shape function, you can use two ways, either by substitution into the equation, or you use the conceptual understanding based on the shape function. It must be 0 along the opposite side to the node. Okay, it must be 1 at the node. Okay, so in this way. After you determine after you determine a line with 0 value, you substitute your nodal coordinate into this line function, and you set it equal to 1. OK， 这是找形状函数的方式。找完形状函数的方式，你就可以求解。OK， 你得到的这个力还相对简单，基本上只有这个 x 方向的力。This force is relatively simple. It's only the uniaxial force in the x direction. So not 0 in the y directions. And now, you go to a matrix, okay? You go to solve this, okay? How to solve this? Let's do the simplification because I don't like the right hand side matrix pre-multiplied by complex stuff. So I move this into the left hand side. Okay, now is my operation of Gaussian elimination. First thing is my first equation. Look at here. This is, we have to diagonalize it so that the bottom is 0. Okay? Gaussian elimination 的这个做法，它的目的就是让这个斜边以下的这个单元全部为零。所以我们第一步是先把第一排第一列的这个系数，除了第一行的以下全部设为零。那怎么弄为零呢？你看这个是1 plus 3。Okay. After 1 plus 3, okay, 我们看一下1 plus 3怎么加？1减负1 0 0加1减1和1减1 minus 1 plus 4 become 3 minus 2b remain 2b plus this one become minus 1 plus 3. So this is the entry after you have done this 1 plus 3. Okay, I mark the line there. So my operation give me this. Okay? And then the second operation give me this. Okay, my second operation is 1 plus 4. Okay, not directly 1 plus 4. Okay? Minus 2b times 1 plus 4. So 1 times 2b minus 1 times minus 2b plus 2b, then 0. This 0 remain. And then this is minus times minus 2b become plus 2b. Plus 2b plus this one becomes minus 1 plus b. This is minus 4b squared, and then adding up to the last row. And then we continue. Okay, because after making the first row 0, but still not happy, we want to make the After making the first column 0, we're going to move to make the second column 0 below the diagonal line. Now it is 2 plus 4, okay? 2 plus 4, okay? The purpose is making the bottom one 0, let me see. 2 plus 4, let's see. Okay, if you see 2 plus 4, 2 plus 2 times, okay, you see here, 2 plus 4. This is positive 1 minus v over 2. This is negative. If I plus it, so this term becomes 0. If I plus this term becomes 0. If I plus this term becomes 4.5. And then minus something, let's see. Yeah, minus 0.5v minus 4v squared. Okay? So in this way now I make this bottom column 0. Okay, but I'm still not happy with this term. I still want to make this 0. Okay? To make this 0, I have minus 2 times 2 plus 3. Okay? So minus 2 times 2.3 times 3. So what I'm entering is this term.